Hi there, Mr. Sutton bringing you the AB Calculus 411 homework solutions on L'Hopital's rule. For this problem, we need to find the limit of this thing if it exists or explain why it doesn't. So we'll start by plugging 3 in here and seeing what happens. So I see that if I plug 3 into my denominator, I'm going to get 0. Do I get the same thing in the numerator? Well, we're going to have 9 plus 3 minus 6, which is not 0. So since this is not 0 and 0, we're going to go ahead and actually plug 3 in for real and see what happens. So we've got, let's see, 12 minus 6 is 6 in the numerator. This is 0 in the denominator. We're dividing by 0, and we don't have 0 on top. So this is a vertical asymptote. So this is dne for the limit. On this problem, we're trying to find the limit as x approaches 0 of cosine of x minus 1 over 2x squared. Now, if I were to just plug 0 in for all the x's here, I suspect I might be getting 0 over 0, definitely 0 in the denominator. So let me just take the limit of each of these individually, and if I have to use L'Hopital's rule, I will. So cosine of x minus 1, limit as x approaches 0 of that. Cosine of 0 is going to be 1. 1 minus 1 is 0, so that limit does come out to 0. And the limit of 2x squared as x approaches 0, that's 2 times 0 squared, that's also 0. So that means that we can use L'Hopital's rule to evaluate this. So I've got my original limit, and I'm going to take the derivative of the numerator and denominator separately. So for my numerator, that's going to be negative sine of x, and this is all as a limit as x approaches 0. And then for the denominator, I've got 4 times x as my derivative down there. And if I plug 0 into both of these, I again think I'm going to be getting 0 over 0. So let me do this dance again. Limit as x approaches 0 of negative sine of x, that's negative sine of 0, which is 0. And then limit of 4x as x approaches 0 is also going to be 0. So I can go another round of L'Hopital's rule on this one. So here was my previous limit, kind of my midway limit here, and I'm going to again take my derivatives and put that in a new limit as x approaches 0. So derivative of negative sine of x, that's going to be negative cosine of x. Derivative of 4x is 4. And now if I plug 0 into this, I'm not going to get 0 over 0. Cosine of 0 again is 1, but we have a negative, so that's negative 1 and a 4, so negative 1/4. On this problem, I want limit as x approaches 0 of e to the x minus e to the negative x over x. If I just plug in 0, I definitely have it in the denominator. So just to be on the safe side, in case this ends up indeterminate, let me just start taking the limit of each side of the fraction individually. So I've got the limit as x approaches 0 of my numerator. E to the 0 is 1. E to the negative 0 is still 1, so 1 minus 1 does come out to 0. And obviously the limit of x as x approaches 0 is also 0. Since we have the indeterminate form with these two zeros, that means I can use L'Hopital's rule. So let me take my original limit, and that's going to equal the limit of the derivatives of the numerator and denominator. So for the numerator, derivative of e to the x is still e to the x. Derivative of negative e to the negative x, that would be negative e to the negative x times a tail of negative 1. So that would end up being plus e to the negative x up there. And then derivative of x is just 1, so that's kind of nice. All right, if I plug 0 into all of this now, I'm not going to get 0 over 0, so that's good. And I'm just plugging 0 into these x's up here. This is just, again, 1 plus 1, which comes out to 2. For this problem, we're trying to find a limit as x approaches 0 of this quotient. Now, if I just plug 0 into the numerator, that's going to be 0. And I'm kind of wondering about the denominator as well. So let me do those limits separately. And if I have to use L'Hopital's rule, I will. So limit of the numerator, if we plug 0 into that, 4 times 0 squared is 0, like we said. Limit of the denominator now. So this is going to be e to the 0, which is 1. That cancels out with this minus 1. And then the only term left is this negative 4x. Negative 4 times 0 is 0. So that limit comes out to 0.
So that means we can use L'Hopital's rule since we've got 0 over 0 here. So I'm going to take my original limit, and that's going to equal the limit, same limit as x approaches 0, but of the derivatives of these two parts of the fraction. So for my numerator, derivative of 4x squared is going to be 8x. In the denominator, we've got e to the 4x derivative. That's going to be e to the 4x times 4. So that's 4e to the 4x. And then this negative 4x is going to come out to negative 4. All right, now if I plug 0 in here, it's looking like I'm going to get 0 over, well, let's find out. Limit as x approaches 8x is 0. Limit as x approaches 0 of 4e to the 4x minus 4. That's 4 times e to the 0, so 4 times 1, which is 4. 4 minus 4 again gives us 0, so we've got indeterminate form again. Well, that means we can do L'Hopital's rule again. So we've got this intermediate limit here. This is going to equal the derivative of its numerator and denominator. Derivative of 8x is 8. The 4 is going away in the denominator when I take that derivative, so I've just got 4 times e to the 4x. That's going to be 4e to the 4x times another tail of 4, so 16e to the 4x. And if I plug 0 in, I'm no longer getting 0 over 0. This is going to be 8 over 16 times e to the 0, so 8 over 16 times 1, so 8 over 16, which we can reduce to 1/2, which allows us to match answer choice B. For this problem, they want the limit as x approaches 0 of this craziness, e to the 2x minus 1 over tan of x. Well, let me take the limit of these separately. This is already going to seem kind of suspicious to me. So limit of that numerator as x approaches 0, we've got basically e to the 0, which is 1, minus 1 comes out to 0. And the limit of tan of x as x approaches 0, tan of 0 is also 0. So this is indeterminate, which means we can use L'Hopital's rule on this one. So my original limit is going to equal the limit as x approaches 0 of the derivatives of those two halves of the fraction. Derivative of e to the 2x minus 1, that's going to be e to the 2x times a tail of 2, so 2e to the 2x, and that 1 is going away. And then derivative of tan of x is going to be secant squared of x. So if I go ahead and plug 0 into the x's here, I'm not going to get 0 over 0. Let's just see what this comes out to. So we've got 2 times basically e to the 0. 2 times 1 is 2. And then down here, this is really the reciprocal of cosine of 0 squared. Cosine of 0 would be 1. Squaring that would still be 1. And taking the reciprocal of that would still be 1. So that's all 1. 1 squared is just 1. So this is all coming out to 2 over 1 or 2, which is choice D. For this one, we want the limit as x approaches pi over 4 of this craziness here. So if I plug pi over 4 into the denominator, I'm already getting 0 down there. So let me just take the limit of each of these individually, and we'll see if we need L'Hopital's rule for this. So limit of my numerator, sine of x minus pi over 4. Well, if I plug pi over 4 in here, I've got sine of 0, which is just 0. And the limit of x minus pi over 4 as x approaches pi over 4 is also going to be 0. So this was indeterminate, which means I'm going to use L'Hopital's rule on this. And that means my original limit as x approaches pi over 4 of all that, I can rewrite that as the limit as x approaches pi over 4 of the derivatives of these two parts of the fraction. So the derivative of sine of all this stuff is going to be cosine of x minus pi over 4. And the derivative of the denominator, that's just going to be 1, which is kind of nice. So if I plug in pi over 4 again, I'll no longer have 0 over 0. I'll have something over 1. We're going to end up with, let's see, this is going to be cosine of 0. Cosine of 0 up here is just 1. So 1 over 1 is going to give us just 1, which is choice D.
For this problem, we've got f and g as differentiable functions. G isn't 0, x isn't 0, the limits of f and g equal 0, and the limit of the ratio of their derivatives exists. Based off of all this craziness, we want to know the limit as x approaches 0 of f of x over g of x. Now, if you remember L'Hopital's rule, the conditions for L'Hopital's rule are that your numerator and denominator limits both have to equal 0 or infinity, but in this case we have 0, and this ratio of derivatives has to exist. Well, we've met all the conditions of L'Hopital's rule. So based off of all of this, this limit is just going to be, using L'Hopital's rule, the limit as x approaches 0 of f prime of x over g prime of x. Now, careful picking your answer choices, because we have an f prime over g prime in choice B, but that's not quite correct. L'Hopital's rule states that this is equal to the limit of this ratio of derivatives. So that's answer choice C, where we don't forget the limit notation.
For this problem, we're trying to take the limit as x approaches 0 of this crazy fraction here. We've got some exponentials, some trig, some polynomial, a little bit of everything in there. So just plugging in 0, I notice very quickly that I'm going to get 0 in the denominator. I'm wondering if this is one of those indeterminate forms. So let me just take the limit of the numerator and denominator separately and see if we get 0 for both. So limit of the numerator, plugging 0 into all these things, e to the 0 is 1, cosine of 0 is 1, 1 minus 1 is 0, and then negative 2 times 0 is also going to give us 0, so this whole thing does come out to 0. Next up, limit of my denominator, this is just 0 squared minus 2 times 0, so that also comes out to 0. So yes, we do have the indeterminate form. The good news is that we can use L'Hopital's in these situations. So I'm going to take my original limit as x approaches 0, and I'm going to just convert that to the L'Hopital's version, which is essentially this thing, but I'm taking the derivative of the numerator and the denominator. So derivative of the numerator, we're going to have e to the x, which is its own derivative. Derivative of negative cosine of x is positive sine of x, and derivative of negative 2x will just be negative 2. For the denominator, I'm going to have 2x and minus 2. Now, if I plug 0 into this, I see right away that I'm going to have 2 times 0 minus 2. That's not going to be 0 in the denominator. So already I know I'm going to be able to finish the problem by plugging 0 into all this. It's either going to come out undefined, or I might actually get a number. Who knows? So if I do plug 0 into everything, let's do my numerator first. E to the 0 is 1. Sine of 0 is 0, and we still have that minus 2 hanging around. And in the denominator, we have 2 times 0 minus 2, so that just comes out to negative 2. So we've got 1 minus 2, that's negative 1, over negative 2, which is going to come out to positive 1/2. So that's going to be choice C. For this problem, I'm trying to find the limit as x approaches 0 of sine of x cosine of x over x. So one thing I'm going to do to make my life a little bit easier on this one in the long run is I'm going to convert this sine of x cosine of x business into, well, I know that 2 sine of x cosine of x is equal to sine of 2x. That's one of those double angle identities. So just 1 sine of x cosine of x is going to be 1/2 sine of 2x. So that's my very first step I'm going to take on this. So now I'm only dealing with sine of 2x instead of having to mess around with two different functions. Now if I were to plug 0 into both of these, I'm definitely getting 0 in the denominator, and well, let me just take the limit of each one. If I'm going to have to do L'Hopital's, I might as well do it legit anyway. So the limit as x approaches 0 of this numerator, this is sine of 2 times 0, so sine of 0, which is 0. Half of that is still 0, so we do get 0 for the numerator, and the limit as x approaches 0 of x, the denominator here, is just also going to be 0. So this is indeterminate, which means we can use L'Hopital's rule. So I'm going to take this version of my problem, 1/2 sine of 2x over x, the limit of that, and I'm going to take the derivative of the numerator and denominator, and this is one place where I really save some time doing this double angle conversion, is that I can now just use a small chain rule instead of having to mess around with like a product rule here. So taking the derivative of my numerator, that's going to be 1/2 cosine of 2x times a tail of 2. So that's going to just be cosine of 2x when the dust settles on that one. And then derivative of x is going to be 1. So if I plug in 0 for x, this is going to be a cosine of 0, which is just 1. And 1 divided by 1 is 1. So that very quickly gives me choice C. For this problem, I'm trying to take the limit as x approaches 0 of x squared over 1 minus cosine of x. So let me just take those limits individually of the numerator and denominator. Limit of x squared, that's going to be 0 squared, which is 0. Limit of 1 minus cosine of x as x approaches 0. Well, cosine of 0 is 1, so this is just 1 minus 1, or also 0. So this would give me 0 over 0. That's one of those indeterminate forms. Since I get that, I'm allowed to use L'Hopital's rule to deal with this. So I'm going to take my original limit, and I'm going to take the derivatives of the numerator and denominator separately and set up a limit with the same x approaches 0 as I had before. So I'm going to have the limit as x approaches 0 of this x squared is now going to be 2x, the derivative. And the derivative of my denominator, that's going to be, the 1's going away, it's getting zeroed out. So we're just going to have positive sine of x. Now the limit of 2x as x approaches 0 is again 0, and the limit of sine of x as x approaches 0 is also 0. So I've got the indeterminate form going on again, which means that I can go another round of L'Hopital's if I want. So taking my intermediate limit and taking my derivatives again, derivative of 2x is 2, and derivative of sine of x is cosine of x. Well, I'm definitely not getting 0 over 0 this time, but what do I get? Well, cosine of 0 is 1. 2 over 1 just gives us 2. So that's going to give us choice D. For this problem, I want the limit as x approaches 1 of x squared minus 1 over sine of pi x. So 1 squared minus 1 is going to be 0, so I'm already a little suspicious here. Let me just take the limits of my numerator and denominator and see what I get. So limit of the numerator, we already said that's going to be 0, 1 squared minus 1. How about the denominator? How about sine of x, pi of x as x approaches 1? Well, that's going to be the sine of pi. That's like asking for the y value at 180 degrees, which is going to be 0. So this would give us indeterminate if we just plugged in 1. So that means we're allowed to use L'Hopital's rule to break this down a little bit more. So I'll take my original limit as x approaches 1, and I'm going to take the limit of the derivatives of the numerator and denominator. So my numerator derivative is going to be 2x, still have limit as x approaches 1. And now for the denominator, this is going to be the cosine of pi x times, using my chain rule, times pi. So pi cosine of pi x. Now, if I were to plug in 1 again, I'm going to get something that's not 0. So let me actually go ahead and do that. So 2 times 1 is going to give us 2 in the numerator. And in the denominator, you'll see where this negative is coming from in a moment here. Cosine of pi times 1, that's cosine of pi, which is negative 1. And we've got negative 1 times pi, so that's a pi down there. And I'm just bringing the negative outside the whole fraction. So negative 2 over pi actually matches one of our answers. That's choice B. For this problem, I want the limit as x approaches 2 of this crazy ln sort of expression here. Now I see right away if I plug 2 into the denominator, I'm going to get 0. And I'm wondering if I'm going to get 0 in the numerator as well. So let me just start taking limits so I can do this officially. So the limit as x approaches 2 of my numerator, this is going to be ln of 2 plus 3, so ln of 5 minus ln of 5 is definitely 0. And then we already said the limit as x approaches 2 of my denominator, 2 minus 2 is also going to give us 0. So this is indeterminate, which means among many tools I can use, L'Hopital's is kind of at the top of the list. So let me take the limit of the original here, and I'm going to convert that to the limit as x approaches 2 of the derivatives of the numerator and denominator. So derivative of ln of x plus 3, that's going to be 1 over x plus 3. Derivative of ln of 5, that just zeroes out because that's a constant. And derivative of x minus 2, that's just going to be 1 for the x. All right, well, I don't think I'm going to get 0 over 0 again, so let me just plug 2 in. I can ignore this 1 in the denominator, so it's really just 1 over x plus 3. And this is going to be 1 over 2 plus 3, so 1 over 5, which matches with answer choice B.